Okay, thank you.
Hello, everyone. Thank you so much for being here, and I'm very happy to share my thesis in progress with you all. I'm working on unearthing the physicality of instrumental timbre, and this is also the title of my thesis. A bit about myself. Right now, I'm a third-year PhD student at LS2N, supervised by Vincent and Mathieu Lagrange. And before that, I obtained my bachelor degree in computational physics and a master degree in integrated digital media in the US. And prior to Nantes, I was briefly working as a research engineer in SteelSeries France in Lille, working on audio source separation on game audio. So here's an outline of my talk today. I'll first introduce the background of this unearthing problem, and then the analysis synthesis paradigm that I'm using to carry out this task, specifically how we parameterize sounds with physics. And then I'll talk about audio distance measures, which is a very important concept to optimize this paradigm. And then I'll delve into the three specific projects that I worked on throughout my thesis. The latter two are still in progress. Three of them are sharing this similar objective, but it's working with sounds of lying in different degree of reality, from synthetic to real sounds. The Merriam-Webster Dictionary of on Earth is to drive or draw from the earth, to dig up, or to bring to light something that's hidden underneath. Unearthing is really a task that's everywhere. Archaeologists may unearth a magnificent ancient city. Human beings may unearth a piece of memory. And friends in our labs are working on medical imagings, and they're trying to unearth patterns underneath noisy medical imagings, in this case, ultrasound imagings, to facilitate diagnosis in the downstream tasks. We usually unearth from a substance elements that constructed this substance at first place. So in the sound domain, when we're unearthing a scalar or a vector attribute of a sound, it can be an identification task. When we're unearthing a complete signal in the waveform domain, assuming that the signal has underwent some certain transformation, such as additive, multiplicative, or convolutional, it can be a source separation task or audio reconstruction task. Sorry, I'm losing the mouse. It's important to bear in mind two things before going into this task. First, not everything can be unearthed. Certain details are forever lost in the process of uncovering. And second, not everything needs to be unearthed. When the detail is imperceptible, or when there's nothing to be found because it's no longer relevant to perception, maybe it's not worth it to unearth everything. So in my research, I work on unearthing physicality from instrumental timbre. The biggest assumption is that any instrumental timbre is a result of a complex interaction between the playing gesture and the instrument. In other words, we try to find an analysis algorithm that decomposes sounds into instrument plus gestures. And during this process, inevitably, each factor, the gesture and instrument, is reduced into a vectorized parameter or a time series of such vectorized parameter. And there should also exist a synthesis algorithm that is the inverse of the analysis algorithm. And in general, we assume that the synthesis algorithm is none and try to learn an analysis algorithm using machine learning. To tackle such a task, we need a large amount of data. And on one extreme, we can use a physical model that allows us access to infinite amount of data, but it has a deficiency, which is that it's a simulation after all, and it's deviating from the reality. On the other side of the spectrum, we can collect sounds in the wild, which has its own limitations in that it's a very labor-intensive work. And in the middle ground, we can have what we call controlled reality, where either we replace the playing with some robotic action that we can repeat in a large amount of times and measure it precisely, or we reduce the instrument itself into a very simplified instrument that corresponds to the physical model as much as possible. So the three projects that I'm working on lie in each of these three domains, and I'll investigate the problem of to which extent is physicality implicit in the instrumental timbre. So our work begins with the classic wave equation, fourth order down to wave equation. It's a versatile formulation in that depending on the dimensionality of x, y can correspond to the vertical displacement of a 1D strain model or a 2D membrane model. It's also easy to, with this equation, easy to separate the instrumental manufacturing and the playing gesture. So on the left-hand side, we have the PD coefficients, linear mass, tension, stiffness, and frequency dependent coefficients that correspond to theta, the instrument of manufacturing. And on the right-hand side is the excitation function or the plane gesture. So in our research, we take x to be 2D and the boundary condition to correspond to a rectangular drum that's bounded at 0. And we use a well-established physical modeling method called functional transformation method to solve it. And the solution lies in the model synthesis form, where it's a summation of however many of modes we decide of sinusoids multiplied with an exponentially damped envelope. And this, I'll play a few sample sounds. I think it's coming from the laptop. You can hear it. Oh, okay. Okay. It's capable of generating sounds of different materiality, and we implemented into a plugin looking like this, and to help us make the data set of synthetic sounds later. And in this task, we aim to retrieve theta, the instrumental manufacturing from Y, the waveform, while fixing the excitation pattern. So I will introduce another synthesizer here. It's sorry, I really need to move the mouse. Okay. It's not synthesizing any instrumental timbre. It's called an AM/FM arpeggiator. But the interest of this synthesizer is that it parameterizes sounds in a way that is rooted in auditory perception. Specifically, the mammal's primary auditory cortex have selective sensitivity to spectral modulation rates and amplitude modulation rates, which are precisely the parameter of this synthesizer. So globally, the sound is an ascending chirp signal. You hear it. Okay. Centered at the carrier frequency FC, and it has a certain frequency slope described by gamma, or I can also call it frequency modulation rate. And it's windowed by a Gaussian function and another amplitude modulation function described by FM, the temporal modulation rate. We'll be using the synthesizer for the subsequent experiments as well, so I thought I would expose you to this sound at first. In this task of retrieving theta from Y is also called sound matching in the sound design world, where sound designers are often faced with the difficulty of trying to reproduce a target sound with a synthesizer in hand. The procedure goes roughly as follows. You have a ground truth theta, which you can make a target sound out of, and the sound matching algorithm will try to train a neural network, f of W, with trainable weights W, to estimate theta hat from the waveform directly. So the question arises in how to train this neural network. One natural choice is to just calculate the mean squared error between the parameters. It's also a very reliable objective since it's easy to compute and guarantees convexity. But is not all the time lying in the right scale to reflect perceptual distance of the sounds. So another alternative is to compute the loss after synthesizing the sound. And this requires an adequate distance measure of audio that reflects perception. And such a measure usually needs transforming the waveform to a time frequency representation for various reasons, which I'll explain later. First reason is invariance. Raw waveforms are really bad measures of audio distances because they're not invariant to time shift. Imagine two waveforms that are shifted by a few samples. L2 norm between these two waveforms will be very drastic, whereas they sound exactly the same. And time frequency representation provide invariance within the time frequency atoms resolution implied by the window length. Second, apart from invariance, there is a need for multi-resolution. So Heisenberg principle states that the existence of a limit to which two variables can be known simultaneously, and in the case of time frequency analysis, these two variables are time and frequency resolution. So differences should all be taken into account for a comprehensive measure of this audio distance. One way to do this is via stacking short-time Fourier transform spectrograms together, calculated with different window lengths. This is called a multi-scale spectrogram loss. It's used in a DVSP paper by Google Magenta back in 2020. So you see, I calculated 3 spectrograms with different increasing window lengths, and we see that as the window size increases, the frequency resolution increases, the frequency band narrowed, and the time resolution widened, as shown in the transient. An alternative way is to use wavelets to derive a more compact representation. In wavelets, the basis function time support vary according to its center frequency. At lower center, higher frequency resolution, and at higher frequencies, the wavelets are short in time and have a smaller frequency resolution. And human ears are functioning exactly like that. Human ears are more sensitive to distinguishing lower frequencies than distinguishing higher frequencies. Thirdly, it's important to have the audio distance measure reflect perceptual distance. So in a paper called "I'm Sorry for Your Loss" by Joseph Turian, the collaborators showed the inadequacy of MSS, the multi-scale spectrogram loss, in regressing pitch content. So this diagram is taken from the paper. This shows that the gradient indicated by the MSS to update the predicted frequency of a sinusoid. The target frequency is at the middle, the 346 Hertz. And if MSS is an effective loss function, then at the left of the 346 Hertz, the gradients are supposed to be negative and on the right positive. But you see from the graph that only when the predicted frequency is close enough to the middle will this negative and positive dynamic happen. Or if you move away from the target pitch, then the gradients are tending towards 0, which is not helpful in regressing the predicted pitch back to the target at all. And at the same time, Masuda matching experiments that using MSS only to train a neural net to regress synthesizer parameters is not converging on its own. And it only works when you pre-train the network with parameter loss and fine-tune it with MSS. For these reasons, we adopt a wavelet-based time frequency representation that we believe satisfy all of the properties mentioned before. It's called joint time frequency scattering transform. So I'll briefly describe how this transform is done. Start with a waveform. You apply a discrete wavelet transform to obtain a scalegram. And then to incorporate local invariance, we would apply a temporal averaging operation onto the scalegram. But then now the high frequency information is lost. So to recover the high frequency resolution, we apply a second layer of discrete wavelet transform along the time axis and the frequency axis to extract the spectral temporal modulation information. And finally, another averaging operation along time and frequency to incorporate the local invariance. So you might wonder how this representation is working as a loss objective. So the last 2 years, led by researcher Cyrus Vahidi, who is a PhD student in C4DM in London, we released a differentiable implementation of JTFS and tried it out for the first time as a loss objective. We used it to regress the spectral temporal modulation rates, the synthesis parameters of the AM/FM arpeggiator that I mentioned before. And we time shifted the target signal by a certain amount to add a difficulty in regressing the synthesis parameters. So in this diagram, x-axis is the amplitude modulation rate, y is the frequency modulation rate, same with this. And the target parameter is at right in the middle. The gradient calculated at the predicted pitch on the surface. So if it were effective loss function, that the gradient is supposed to point towards the middle. So you see that the optimization landscape of using JTFS is having a good converging behavior, whereas MSS is the gradient is pointing at random directions, and it's inevitably failing the task. And also combining AM/FM arpeggiators' relevance to auditory perception, we believe that such a strong indication, we show the strong adequacy of using JTFS to represent the audio distance between AM chirp signals is a good sign that JTFS is a perceptually relevant representation. So to summarize, we settled on using JTFS for its excellent properties of invariance, multiple resolution, perceptual relevance, and differentiability. Now the disadvantage is that it's super slow to compute, let alone doing backpropagation through the representation. So this computational constraint led us to proposing a novel loss function, which is the optimal quadratic approximation of any L2 spectral loss. This method largely encapsulating the perceptual information into this matrix, kernel matrix M, and pre-computing it before training and loaded from memory during training. And this accelerates the method much more than backpropagating through the loss function directly. So in the following slides, I will describe how we derived this. So first, we express the usual L2 spectral loss. Phi of G of theta is the spectral representation, or the JTFS coefficients of the estimated sound. And same with the other one. And we apply Taylor expansion of onto the predicted sound spectral representations at theta. We group the higher, we keep only the first order difference, and we group the higher order errors into big O notation. And we move the first term to, we move the first term to the left, and such that on the left-hand side appears exactly the spectral loss, L2 spectral loss. The first term we call PMP loss, and there is also a remaining higher order errors. So given that theta and theta hat is close enough, the higher order terms is negligible, and PMP forms a close approximation of spectral loss. We can rewrite it into a bilinear form, which arrives at this kernel matrix M, and the expression is Jacobian transpose Jacobian of the spectral representation with respect to the theta, to the ground truth theta. This matrix is positive semi-definite, and PMP, this form can also be related to other common loss functions by taking M to be different types of matrices. For example, if you replace M by identity matrix, you get a P loss. If you replace it by a diagonal matrix, you get a weighted P loss, the parameters each weighted by a scalar. So in the case of PMP, there will be off-diagonal terms as well. Approximately the same formulation, except the Jacobian matrix is evaluated at the predicted theta, which requires another computation at every time the gradient is updated, or every time the weights are updated. So this method is really slow. So we went on and applied this PMP loss function onto our drum sound matching task. And in practice, from our preliminary results, this can be explained by looking at the eigenvalue distribution of M matrices in our data set. So each sound with different theta will have its own unique M. And so we calculated this M matrices for all of the sounds in our data set and sorted the eigenvalues and made this distribution. The eigenvalues lie in drastically different ranges, and the M matrices have quite high condition number, which makes and it introduces numerical instability to stochastic gradient descent and gives the neural network a hard time to reach convergence. So to address that, we introduce a corrective term to the M matrix lambda I. This method can be seen in two ways. One way is that we are improving the condition number of M matrices by adding this constant lambda to each of its eigenvalues. And now the condition number is drastically reduced. And another way of seeing this serialization term. And when lambda is taken to be very big, then this term dominates, which is roughly a parameter loss regime. If you take lambda to be 0, then you are back to the spectral loss regime. How did we select which lambda to use? We tried a few different methods, and we settled on using this adaptive damping approach, where we would initialize the lambda at a very high value, roughly the same scale as the biggest eigenvalue in the data set, and gradually reduce it by a certain amount when the epoch validation loss is reducing. So this is like gradually transitioning from a parameter loss regime to a spectral loss regime. This is our results. So we applied this loss functions onto the two synthesizers that I mentioned before, and we compared several state-of-the-art loss functions loss and BDSP, MSS spectral loss, and then the work of Monsieur and Saito, where they pre-trained with parameter loss and fine-tuned with MSS loss, our method PMP, and last year we tried also pre-training with P loss and fine-tuning with PMP loss, and our method has outperformed all of the rest of the method on two metrics. We used the MSS and the JTFS. So there are some sound demos of how several target sounds work under different loss functions in this accompanying website. We also have a GitHub website. And we also did an ablation study where we studied the deteriorating effects of removing H factor in our proposed method. And so I'll just introduce each line. This is our proposed method. The factors are removing pre-training with parameter loss, removing gradient clipping during optimization, removing min-max and log scale, min-max scaling and log scaling of the parameters, or replacing JTFS with MSS in the spectral loss of the fine-tuning stage. So we discovered that JTFS is quite essential in the success of such a task, because you see that removing that has the most effect on the performance. And gradient clipping is also another quite essential trick to do. And we plan to investigate why that might be the case in the future work. So next, coming on to the second project that I had, where we work on sounds collected from controlled reality. So we decided to take this machine listening algorithm onto recorded string sounds. To do that, we fabricate a monochord string instrument that resembles the physical model. We will record sounds from a collection of different strings from different cultures and material, and have access to their ground truth physical parameters. And then we will apply the machine listening model onto these sounds and test their ability to regress the true physical parameters from the sounds. For that, we have curated a data set of string sounds varying the tension, the length, and the linear mass. Their pitch lies in the uniformly lies in a range of around 50 hertz to 2000 hertz. And we have recorded 1 hour of audio material. And however, now we are currently encountering some unexpected issues while validating the data that we collected. So I'll explain this in the following slides. Before I explain the discrepancies, this is a picture of the bench that we built in LS2N by engineer Stéphane Jolivet. The length, and we are using a guitar plug to activate the string. But we have this small mechanism where we can fix the initial displacement of the string and release it. One potential problem, or this is not really a problem, but it's something that is inevitable from this formulation, which is that we can't really measure all of the PD coefficients of this physical model. We can measure tension, length, linear mass, plug height, plug position, but its stiffness D1, D3 is theoretical. It's I'm not aware of any method to measure that directly. And stiffness, we are lacking tools to do that. We could look it up from the internet, but it wouldn't be too accurate. But this doesn't impede us from comparing the physical measurables that we have access to. So here is the problem that I was talking about. During the data validation stage, we wanted to test the recorded string sounds consistency with the simulation by first and foremost verify the fundamental frequency. I have the two equations. The first one is indicated by Masson law, and the second is by the FTM physical model. They are similar in that if you take the stiffness and the damping coefficient to 0, then they predict the same pitch. So we try to see if our sounds are the fundamental frequency of our sounds is exactly according to the formula. And there's a summary of what we arrived at. So around half of them have the correct pitch, exact correct pitch predicted by Masson law, and but there are 100 that are higher by a whole tone. There are also sounds that are higher by a minor third, a major sixth, a perfect fifth, a minor third, and we thought about the potential off by a little bit. It might be due to an inaccuracy of the tensiometer reading, because certain materials are quite elastic, and they cannot withstand a tension that we designated. The highest tension that we designated is around 80 Newton. And for the simple instrument setup that we had in the lab, it was quite a stretch to reach that tension and to still hold it, and it slips a lot. So we thought that maybe we can adjust the tension after the tension reading afterwards according to the pitch that we hear from the sound. But then this wouldn't work for the ones that are off by a larger amount. So we will be very grateful to hear if in an acoustic lab like yours, you have encountered similar issues like this. So in the immediate future, we would like to filter with Masson law before proceeding with a few other plans on domain adaptation of the machine listening algorithm, because to apply this machine listening algorithm onto this recorded sounds is it will be an issue of simulation to is a commonly existing problem in deep learning community. This notion of synthereal, where large networks are trained with synthetic data but have issues transferring the knowledge to realistic sounds. So there are some issues in the sound that we need to address later on, like the noise or the partial strength and the partial spacing might be different from the physical model. Finally, briefly on the last project that I worked on, which is on a Chinese scissor instrument called guqin. It looks like this. It has 7 strings and it's a plucked string instrument. It's a very ancient instrument with the right hand plucking, and the left hand can either leave it as is or press the string to modify the pitch and slide along it, or to just lightly brush it to produce harmonics. The interest in studying this instrument is there's a historical significance. There's also that it's quite relevant to study the gesture of this instrument, because the hand is directly interacting with the string and the soundboard. And the gestural influence on the timbre would be quite immediate for this instrument. So we selected a few sound types and derived the important gestural degrees of freedom that influence these timbre from an ancient treatise written in the Tang Dynasty around 1000 AC. These gestural degrees of freedom would be what we try to unearth from the sound. So we have for each sound type, the gestural degrees of for example, for almost all of the pluck string sounds, the pluck position directionality of pluck, the finger used would be gestural degrees of freedom to study. And for harmonic sounds or vibrato or press string sounds, then the left and right hand timing and the mode of contact, whether it's flesh that is contacting the string or the nail that is contacting the string, will make a difference on the timbre of the sound. So after we curated this playing techniques and sound types, we captured the audio and the gestures in a data set of around 3 hours, which happened right here in this lab last August, thanks to your generous support. We used the 2 GoPro cameras to zoom onto the 2 hands and 1 Canon camera to have 1 contact mic attached onto the soundboard and 1 condenser mic on the top. And we also have this experimental measurement where we placed 2 accelerometers onto the player's hand and 1 other accelerometer underneath the soundboard as a way to infer how much force is the player exerting onto the board by calculating the correlation of the signals received from the accelerometers. Oh, so after process to know which extent is gesture implicit in the sound and carry on with the subsequent tasks. So the data validation lies in the form of both computation and perceptual test. On the perceptual side, it would be interesting to know if the guqin players themselves are able to hear the underlying gesture. For example, if I play a pair of sounds to the player who is playing this, who is making this data set, will she be able to tell which away from switch, or will she be able to tell the directionality of her pluck, or the finger use even? So this listening test is underway to learn more about their capability, and we also plan to recruit some guqin students to test their ability to listen, to hear the gesture, underneath the sound. And after this validation, the plan is to study the correlation between sound and gestures you see these are all a technique called TL using the index finger to pluck outward. But there are minute differences in the way the prefix and the suffix, which are the gestures as before the sound has happened and after the sound has happened. There are a lot of variations that could be interesting to summarize and study. So in terms of what type of correlation that we would like to study, the topics may vary, and it really largely depends on the quality of our data. So some examples might include studying the asymmetry in time for sound and gesture. There are some previous work on studying the time lag of the prefix of the gesture and the sound that is influencing at a later time. Or there are methods like CCA, canonical correlation analysis, that learns a transformation onto the gestural feature and the sound feature such that they are maximally correlated. And then we could look at the learned transformation and try to interpret it physically. Here I'm just talking, this last part is about the data validation process, the computational way of validating the data that we collected. So that took on the form of map making. We first compute a certain audio feature, in this case, the CQT coefficients. And then we use a tool called isomap to compute a timbre map. This is a classic timbre map proposed by Stephen McAdams that places timbre into a high-dimensional space, and where the placement of the sounds is determined by their distances. The closer the two sounds are, the closer they're placed in the space, and vice versa. And then some dimensionality reduction method is applied to facilitate visualization. And we aim to use this to place the sounds that we recorded into a map and see if to validate the separability of timbres with different gestures. So is it true that sounds of the same gesture lies closely with each other, and vice versa, if there are clear clusters formed in the map? And I'll hereby show a few examples. So this one, string pluck sounds in the data set. They are of the same pitch on the same string, but pluck at 5 different positions. And they could also be produced either outward or inward with one of the 4 fingers. So I put them into a map and I colored them first using the pluck position. So you see that these colors are well separated, which shows that pluck position in our data set indeed have an effect on the timbre. And the same procedure is done for the pluck directions. I colored the outward plucks with red and inward pluck with blue. And the cluster are still formed, but they're within the clusters that's formed by the pluck positions, if you compare it with the previous graph. So each of these clusters will have a subcluster of outward and inward plucking. And lastly, I colored the sounds with finger use, and it's not distinguishable at all. So yes, in conclusion, I showed 3 projects and their possibility to unearth physicality from instrumental timbre, and they work on synthetic sounds, sound recorded from control reality and reality. And with that, I end my presentation, and thank you all for your attention.
You have to speak very loud so we can hear it. So you talked about measures on strength, and I'm not sure I got all what you said about the stiffness, because I understood you said that stiffness is harder to density and parameter. So, but I did not get what you ended up doing.
So that would be the part that I leave out and not as the physical measurables. So this is right here. So I said that well, the resources that I have access to currently do not allow me to measure the Young's modulus or the moment of inertia, which correspond to the stiffness of the string. And so but I still have access to other measurable physical parameters. So during my validation process or when I'm testing the accuracy of the retrieval, I would skip the stiffness and just focus on the other ones. Because I don't think it's reliable to look it up from the internet. These.
So it's not directly measurable without some inspection tests. So you can get it from dynamic measurements by looking at the economicity of the string.
Okay.
But it's not a direct measure. You are fitting a model of the economicity of the string.
Okay. All right.
And it can be open.
Okay. Yes.
Related to the first project.
Yeah.
And if correctly, you're presenting a perceptual metric to optimize your bits. Do you have any we designed that new metric and now we test it compared to what people think are actually the distances between the various theta of the sound we've synthesized?
You mean having people
perceptual validation of your perceptual metric?
I haven't done research like this, but Mathieu and Vincent has I think human ratings of temporal distances and found and compared it. There was not only JTFS distance, there was also I'm not sure which other deep embeddings, and arrived at the conclusion that JTFS is the most correlated with the human ratings. Yes. Yes.
I didn't really understood the in particular, I don't really, because you say with the NSS, so it's just the distance between the two spectrograms. So you have problems with the estimation of the pitch.
Yes.
And I didn't really get how did you pass the difficulty with
how do I pass the difficulty with JTFS?
Yes, with the pitch. Because for me it's more or less
yeah.
So in fact I don't really get the difference with
right.
You have some averaging times
yes
frequency.
I can only explain from the it's true that I cannot offer much theoretical intuition to how this would solve the pitch problem. I'm sure that the pitch problem still exists in using JTFS to regress the predicted frequency, but from empirical results that we arrive at that conclusion.
And does exist some distances which use time correlation? Because I know that some pitch detection algorithm use autocorrelation of the signal. Do you know some distances which use that specifically to deal with the pitch?
No, not that I know of, but I can. Okay. Not really sure. Yeah.
I may add just one little comment that those would be prone to octavariance, meaning you would have a lot of local minima. Okay, So yes, indeed, if you are starting one semitone apart, migrating cent, you will fall into global minima. But if you start one octave and one semitone apart,
you have minima at the octave or the pitch.
Yeah, so this is currently an open topic. I mean, there are papers coming in on this idea, and maybe they will things will change in a year or two. But right now, at the moment, we're not really confident about regressing the fundamental frequency from spectrum. Believe it or not, this is tough for us to train a neural network to regress speech. Yeah, like what did you say?
Maybe, but I don't really get what is the motivation of this work. Is it to make numerical instruments, or it's to provide tools to?
I think in the case of sound matching, it's quite needed in the industry for plugin makers, because in reality the plugins can have a lot of parameters that have intermingled effects on the sound, and it can be hard for inexperienced people to find the optimal combination of parameters. I know certain plugin companies are trying to find an algorithm that would allow them to have the users initialize at a preset that's predicted by some algorithm that arrives at a suboptimal solution to sound. And other than that, just the problem of disentangling effects of instrument manufacture and playing. I think it's helpful for building a ergonomic instrument, a digital instrument, virtual instrument. Because there's increasingly there are drum pads or digital instruments that are being built, and it will be important to see, to correlate which type of gesture in reality would produce what type of sound, and these type of knowledge can be translated into these instrument makings more. And then yeah.
Third project, do you have any idea how you avoid the overfitting of your analysis to a given instrument?
Overfitting, which overfitting?
Like you draw that space of like that's the plug sum and tension and the way you plug it. How do you you have access to only one instrument? Can you predict and can you say, yeah, that's space and that's slicing of space will, sorry.
The third project, to which tension are you?
Pronunciation of that instrument. Okay. But do you have any idea how, more I give you another question, how it varies and whether or not this variation is actually within those blueprint and all these areas? Because if I give an instrument which variation is like so big that basically your problem is like you can't even, not knowing the instrument beforehand, now tell, oh, that thing is coming from like me pinching it. I'm sorry.
So you're talking about, now I have this very few samples that I formed this map, and if you introduce something that's like same cluster, that was a question. There's a way to place the sound into the map for sure, but I agree that because of the forming of this map is based on mutual distances, and if there's one sound that's quite far from the rest of the sounds, and it distorts the entire spatial arrangement, immediately you might end up with some sound that's here and the other sound.
The whole cluster that's just like
yeah.
And then you would need some kind of calibration procedure beforehand so that your network with like 10 samples flagged. Oh, that's this type of instrument, and you test it.
I think depending on if the goal is to classify what gesture is underneath that newly introduced sound, then maybe this method is just not the right way to go. You would need the things that come to mind is certain domain adaptation to transform the sound that you are querying more corresponding to the sound that is existing in the corpus. But otherwise, this approach just doesn't immediately work. It's not having this map. The purpose is not to have a query system, but rather to validate what is existing already inside the data set. Yes, yeah. But your problem would require another solution. I'm not sure if that answers. Yes.
I understand that you tested the boot chip, which is a curved instrument, so the interaction between the musician and the instrument is quite, localized in time. Would it be possible to follow the gesture of a continuous interaction, like bowing or singing?
Just studying in terms of studying the correlation, or
yeah, in terms of characterizing the gesture.
Oh, you mean what type of feature would I use to characterize a continuous motion?
Yes.
Right. Yeah. So far, I only talked about quite discrete descriptors of the gestures. It's true. So yes, the next plan is to do the continuous tracking. So I use GoPro camera that limits my approach to tracking the movement into computer vision. So it's definitely not as convenient as having access to the motion capture data that you don't need to really calibrate the coordinate system anymore. But I thought about several approaches. I read some literature, which there are some measures that quantifies the jiggedness of the movements, and how spread out the coordinates that are tracked are, or how contract. I guess there are some measures that you can reflect the openness of the hands, and there's also the smoothness of the gestures. I think whichever features that I settled on using, it will be coming from what hypothesis that I want to test with the sound.
But still, I mean, so this would be to take into account a more detailed fine gestures, because you just answer just a click. It's actually something before, something after, or but I think this question as well, like when you have a continuous gesture like bowing, you actually adapt your bowing, you know, along the sound. So
okay.
Something that you
test the string.
Yeah. This the question of I understand more your your question now. Is there any gesture that is modifying the sound while the sound is produced?
Exactly.
To be honest, the data set or the playing techniques that I selected out of this treatise do not have obvious. Is not falling into this category of gestures. There are vibratos or glissandos in the sound, but it's usually just defined as, do you want to hide the beginning pitch or not? And that would be or how do you want to for in terms of vibrato, what is the contact point of your finger to the string, and what is the fluctuation of your movement to the sound? But all of these is predetermined before the player make the movement. They don't really adapt while they play.
But is it something that you could, when the question was like, how would you incorporate that to your model afterwards to be able to unearth the gesture?
That's a difficult question.
And do you think it's possible?
I think as long as I have pairs of gestural and sonic data, the intention, whether there is intention or not, does not affect how I study the correlation. Like, it's fundamentally different, the two types of gestures. But if I focus on the gestural, if I just focus on the correlation between what is actualized in the physical world, then the intention does not impede from analyzing those correlations. Yes.
Do you evaluate the variation of function or Nancy?
In the Mersenne? You mean the routine or the
Mersenne?
Yes. Right.
Do you evaluate this?
Not in my direct measurement. I did notice that because there was pitch bend in the Mersenne recordings, and the tensiometer reading was also fluctuating a lot, but I did not have any mechanism to record these fluctuations as well. I had only an initial starting tension and the sound. It was due to a limitation of my experimental setup, but and in terms of routine, I didn't measure retention. But that could be a cost, one of the causes of why the pitch was inaccurate. I think that would apply to sounds that are a little bit off for Mersenne law, but not the ones that are fifths apart or sixths apart. Well, can I explain why this difficulty appear?
Due to the variation of
But someone for you to have a six. No, the six is at the end. It's when you say that the pitch, it's a pitch after the transient. Basically, the pitch you get after.
Yeah.
After if there's any pitch bending, you don't take into account. This is when you say it's a major six, that's after the pitch bending.
The pitch bending is not that apparent. It wasn't like it was just I mean it wasn't first. I agree that first. Yeah. There wasn't too noticeable pitch bending happening at these.
I think it's quite soft.
Yeah.
You don't display it by greater.
Yeah.
Even soft.
Okay.
Yeah, but can that explain the?
No.
And have you had that in your experiment with the
damping is dependent of the frequency or not?
No.
But she didn't use any damping in a.
I wasn't estimating any damping in the.
Estimating the picture in this formula.
I didn't compare the damping. It was yeah, I was using the first formula because I didn't have access to this. These would theoretically have an effect on the pitch bend, but it wouldn't bend it out that amount by that much as the major six.
Can it be due to the boundary condition? Maybe?
So the two both ends are fixed, and which is corresponding to the physical model.
frequency is the same. The string is the same. You the same tune for the string for what they sound.
No, no. They are uniformly sampled between around 50 hertz to 2000 hertz, and so these deviations.
Just change the string. She does change it.
I would say check if those discrepancies happen in blocks or all across. If blocks, it's just
yes. If it's off by for example, if a string is off by a minor third, then all the takes of this string will be off by a minor third, no matter what length, what tension.
Tension for string that would change. The other thing that I can think of that changes the note that much
is the tension.
If it's the length, someone is just like blindfolded and doing the experiment, and you probably you would have seen it.
Yeah.
I would say the tension is the only thing that can change.
Okay.
Yeah, but that means that the tensiometer is not measuring.
I just see 3 terms on that equation, and I do like based on like when you plug a string, the only thing that can change that much is 6 and stay consistent within time. For me, it's tension.
We thought that might be possible, and we thought that using this setup to measure tension might just the rest of the strings the tensiometer reading is apparently accurate. So we're really not sure why certain strings tension is measured accurately and the other ones can be off by so much.
The tensiometer is attached to something that is attached to the string, right?
It's actually directly hooked onto the tensiometer.
The string is hooked on the tensiometer.
Yeah, and the tensiometer is fixed onto the bench.
Okay.
So it's a fixed amp.
Ours is the
nuts. Yeah. The nuts is quite fragile.
It's a sensible point.
Yeah.
Sensitive.
Six encore une fois.
Non, mais pas avec tous les éléments.
So you think that if the note just spreads a bit more, that could change the tension?
The next slide, I don't understand the second.
This is the equation. This is the solution from the FTM solver. So, okay.
It's not homogeneous.
Huh? What?
Yes.
What do you mean?
Because D1 and D3, you have to divide by mu if you si elle prend l'équation d'avant.
There is a mu missing divided by 4 mu.
It's possible.
But
how does this derive? I have to show you the solution of functional transformation method too, because the functional transformation method will have a model synthesis form of solution, and there will be amplitude coefficients Km, exponentially damped coefficient sigma m, and omega m. And this is the expression for omega m when m equals 1, which corresponds to the fundamental pitch. And the solver will have an expression for Km, sigma m, omega m expressed in terms of the PD coefficients. And I have to show you a lot of more equations to tell you how this is derived.
But you haven't even used it anyway.
I have what?
You haven't used
I haven't used it, yeah.
You didn't use it.
Ça m'a vu le carré, je comprends, le terrain, le carré, tu regardes
Mais de toute façon, en fait, elle n'a même pas utilisé tous ces résultats-là en utilisant ce duo. Mais est-ce que de rajouter le fait qu'il y ait du module Young, est-ce que c'est ça qui pourrait expliquer
le module Young, ça va t'apporter une harmonicité, donc ça compte pas pour les autres.
C'est ça.
Non, pas pour les autres. Non, parce que dans l'équation, c'est racine de 1 bêta.
Oui, c'est ça.
Donc n niveau 0. Nous, on est capable de...
Oui, donc du coup, la première formule devrait marcher.
S'il n'y a pas de variation.
Et c'est pas ça qui peut, c'est pas le fait qu'il y ait un peu de raideur qui va te donner ton tour des cartes.
Non, et vous l'avez fait à l'accordéon ou pas?
Mais non, ils mettent une certaine tension et ils mesurent le F0.
You mean before?
Ah oui, mais le F0, c'est ce qu'ils obtiennent.
Yeah,
tu voudrais dire que le calcul du F0 correspondrait pas à ce qu'ils ont entendu quand ils ont fait l'expérience, c'est ça?
We definitely tried that, but then it was too off, and we needed to collect data in. We had the time constraints, so we decided to just proceed with the recording and figure out the F0 discrepancy later. But going into the recording, we knew that the F0 is quite off.
And the sensor to measure is only the tension, or you have an accelerometer or microphone?
I have a microphone, yes. Yeah.
And you use the data of the microphone?
Of the microphone, yes. The condenser microphone. We actually did it by listening.
And it was the same?
Yeah, because we know that certain pitch estimation is not accurate. So we will. What do we do?
Yeah, so I think that was his question when you said like it was a tuner. So you did by listening and it was the same.
So what we had is that we had a low frequency oscillator. So we would look up the values of L, T, and mu, program this oscillator to play back at a certain hertz, and then compare with what we hear from the microphone. And then we would measure intervals. So this is how we got to this table of intervals. And those intervals were measured by musical speed. It's like, no, we weren't being very mathematical about it. We were musical.
In your setup is correct. You don't listen. You don't listen.
While I
because your equation it's fixed.
So you see that the difference could be due to the boundary conditions.
For that, better to use a sensor, optical, or accelerometer to have a better signal to noise ratio.
Okay. Accelerometer is measuring what? Measuring the acceleration of the displacement.
Acceleration at the end of the string.
Oh, okay.
And where do you plug the string? Is it not on?
It's around here. So, 20 centimeters.
This is more or less the setup of a guitar.
In the test of the guitar, on the electric guitar, it's a very good.
You could put
the
strings you could put the strings on the guitar.
On the next
Yeah, but then you don't.
An electric guitar.
But then you can't measure the tension.
With the frequency. It's very difficult to measure.
So probably the measurement is off. Tension measurement is off.
The precision of the. To have a good precision, you have to develop your concepts with the one concept. Because I don't think that Internet is
I think.
It's designed for this.
Right, yeah.
So you would suggest that the tension should be estimated by the pitch.
Yeah.
Which is what
Which is
usually done.
Right, yeah.
You measure the pitch, and from this you deduce the tension.
Yeah, but that's kind of the
mu, the linear mass is easy to have with
the scale. Yes.
Yeah.
But in the string, D1 and D3 are dependent on the distance. And it's very, very important, this dependence here.
Oh. Usually, right? Or
yes,
is it?
there are much of work, but you have to by fitting a model of the
on a variety of sounds on the same string.
Yeah.
Okay.
And the D1 and D3 are dependent on the tension. Dependent on the frequency of dependent.
Yeah. So these terms are actually varying when I'm extracting it from the sound. T and D1, D3 are interdependent.
But model is not. Don't choose this kind of model because it's a sort of viscous thing. So I think it's not this. How do you find this kind of equation?
I found it via the physical modeling method that I was talking about, the functional transformation method. They work on solving this. They transform this equation into functional spaces, Laplace transform, and then Louisville transform, and they have a closed form solution for y in the functional space, and they could
string.
Yeah.
We have correct some modification like stiffness or damping. We use the equation and we add some extension.
Okay.
Well, I think it's time to Thank you.
Thank you.